Hey, this is Mr. Aspel, and we're going to talk about where electrons are found in the atom and how we know they are found there. First, we're going to look at this thing called the electromagnetic spectrum. The electromagnetic spectrum is sort of an energy spectrum, and there's all sorts of different types of energy. There's energy that comes from the sun, and that gives us usually white light, but if you put white light through a prism, it will split into all the colors of the rainbow: Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. Okay, there's other types of energy, which is sometimes called electromagnetic radiation. Light also, by the way, is electromagnetic radiation, these regular sunlight. There's other forms of energy like microwaves, or you guys know you probably have a microwave at home, or satellite waves that come in, um, AM, FM, stereo, television waves to run your television. So there's waves, energy waves to um, all over us, to energy waves that are connecting us by cell phone. And some of these waves have more energy than others. Um, though I want to talk about a couple different things. So first of all, there's also infrared waves. Infrared waves we cannot see unless we have night vision goggles. Sometimes, like the Army uses night vision goggles, and that shows the heat given off of a person. That heat given off, you're giving off heat constantly. And at night, you can't see anything because it's dark out. But if you have night vision goggles and you can see the infrared radiation or heat given off by people or animals, you can see that heat, which is the infrared radiation. Okay, ultraviolet radiation we also can't see with our own eyes. It has more energy than visible light, and that ultraviolet radiation is why we put on sunscreen. And luckily for us, there's an ozone layer high in the atmosphere that blocks 99% of the sun's ultraviolet radiation. But the 1% that does break through and get through the ozone layer, we have to put on sunscreen to protect ourselves from this really high energy radiation so it doesn't hit our skin and give us cancer eventually if we get enough of it. There's also x-rays, which you know are good if you have a medical issue, but you shouldn't get them all the time. If you have too many x-rays or lots of x-rays all the time, that can affect your cells. And sometimes these higher levels of radiation are known to cause cancer, ultraviolet radiation like skin cancer, medical X-rays and radioactive sources like gamma rays, cosmic rays, or like if you're exposed to like a nuclear power plant or a CT scan in the hospital, that has gamma rays. And so if you're exposed to these things, like the higher level of exposure and the more you're exposed to them, the higher chances of getting cancer and it messing with the DNA in your body. So we're going to focus on this part of the electromagnetic spectrum, the visible portion, Roy G. Biv, and we're going to talk about how a scientist named Bohr used the electromagnetic spectrum to figure out sort of what was happening to electrons in an atom. So here is what's called the emission spectrum of hydrogen. Okay, what did Bohr do? So first of all, Bohr took electricity and he ran it through a hydrogen lamp. This hydrogen lamp had nothing but hydrogen in the lamp, just hydrogen gas in the lamp, no oxygen gas, nothing else, no air, just hydrogen gas. So when running an electrical current through there, it gave off light. And if you see this light, it would look pinkish purple to your eyes. But if you ran that light through a slit and then you had a prism on the other side of the slit, that light would actually break off into really specific colors, being red, blue-green, blue, and violet. And those specific colors have very specific wavelengths and energy. And by the way, the closer you are to infrared or red, this means you have less energy. And the closer you are to violet, that means you have more. So this purple means, or this violet means a lot of energy. If you have that sort of smaller wavelength, it means you have a lot of energy. And if you have a larger wavelength, it means you have a lower amount of energy. Okay, I sort of want to talk about why this is. So you can think of yourselves at the beach and just hanging out, and let's say you have some waves coming at you, and the crest of these waves, the distance between the crest of two waves is called a wavelength. So even ocean waves have a wavelength. So if you're at the beach and you have like one wave hits you, let's say that this wave hits you, and then a minute later this wave hits you, so you might like fall over, get up, and then the other wave hits you a minute later, but you're able to recuperate because it's a minute in between waves. Well, now what if you have a wave that has a shorter wavelength, but it's the same height as the other waves? So look at this wavelength. Okay, and if you're on the beach, and let's say these two waves, it took a minute to pass, and all 6 of these waves happen in a minute. Well, it might be every 10, 20 seconds, you're just pounded with waves. You like get hit, get up, get hit, get up. So if you have a shorter wavelength, this wavelength is shorter. The distance between those waves is shorter. So the shorter the wavelength, that means the higher the energy for this wave overall. And if you have a longer wavelength, then so wavelength is this symbol. It's sort of like an upside down Y. It's called lambda. If you have a higher wavelength, then your energy is lower, or if you have a longer wavelength, I should say, your energy is lower. So I want you guys to remember that longer wavelength, energy is lower. If you have a lower wavelength, your energy of your wave or waves are higher. So that being said, on the electromagnetic spectrum, you can see over here, here's like longer waves. And so longer waves are, red, the color red and beyond, infrared, etc. So red is going to have like a longer wavelength. It's going to have lower energy waves. If you have ultraviolet, or you're closer to violet, or beyond, then you're going to have higher energy waves over here. Okay, so what do all of these energy waves mean that Bohr saw when he had the hydrogen lamp go through the slit in the prism and emit these 4 different wavelengths of light? Well, what he thought was happening was this. There's a nucleus to the atom, and hydrogen, he thought, had 1 electron. And he thought, this electron, what is it doing? Well, for this red wavelength, which has very little energy, he thought the electron was jumping up to a different energy level, maybe to the 2nd energy level, and then that electron was jumping back down. And when that electron jumped back down, it emitted what's called a red wavelength of light and gave off light. So if in another instance, and maybe it was like less than a millisecond later, the same electron, which had jumped back down, jumped up even higher to another energy level, and then jumped back down, this is going to emit a green wavelength of light. As you know, green has a smaller wavelength, so it's more energy. So that's green light that's emitted. He thought the same thing was happening for the blue and violet light, that the electron was jumping up to a higher energy level and jumping back down to emit blue light and to eventually emit violet light. I don't have a violet color, but it goes up here, and that's another, energy level, and that would emit violet light. So I want to review this one more time, but with the metaphor of a ladder, because it makes a good metaphor for what's happening to the electron. So let's say the electron, sort of lives or spends most of its time right here in what's called the 1st energy level. So this is known as its ground state. So wherever the electron normally is found, that is called its ground state. So for a hydrogen atom, its ground state is the first energy level. Now, in order for an electron to jump to a higher energy level, all of these required energy. So it requires energy in order to jump up. Where did it get this energy from? From the high voltage electricity going through the hydrogen lamp. So that's where it got its energy from. So it requires energy to have an electron jump up, right? Okay, when it's in these other energy levels, and when it jumps up, these other energy levels are called excited states. So like for example, when the electron is here in that second energy level, it's in an excited state. Normally it's not in an excited state. Normally it's in its ground state. But sort of like if you, for example, jumped up and you jumped up on a ladder and you like then landed on this rung of a ladder, but then you like quickly jump back down to the first rung, then you were in like an excited state for like a second. You were higher for a little while, but then you had to jump back down. All right, when it jumps back down, that's when there's a release of energy. That release of energy is in the form of light, right? Red, green, blue, and violet light. Okay, so ground state we're going to say is the first rung of the ladder. An excited state would be the second rung. A different excited state was if the electron even had more energy from the electricity. Sometimes it jumps up here, jumps back down to its ground state, jumps back up to the higher energy level, fourth energy level, jumps back down to its ground state. Every time it jumps back down, releases light. Every time it jumps back up because it's still getting voltage from some power outlet. Okay, these black spaces these are called emission spectra. When you read this like line of colors and their wavelength, this is called an emission spectra or atomic emission spectra. And these black spaces are really important. Why are these black spaces really important? Why is there not any different colored light in these black spaces? These black spaces means that electrons cannot jump from the first energy level to like a quarter of the way up to the second energy level and back down, or can't jump up halfway up to the second energy level and back down, or 3/4 of the way, or 90% of the way. It cannot do any of those. If it did those, all of this would be filled in with light colors right here, but they're not. So it's really important. The electron is never really found in those areas. It's only found in the areas where light is emitted, or where these different wavelengths of light is emitted. That represents sort of like the distance between those energy levels. And this is how Bohr and other scientists found where electrons were in the atom.